And now we will be discussing some cipher techniques, because we have been telling about ciphertext so many a times. And definitely we are curious to know about this ciphertext. And what is the ciphertext? Basically, it is the encryption, transforming the plain text into an encrypted data, so that if any attacker steals that ciphertext, that encrypted data also, we are happy. We are not at all concerned, because we know that he will not be able to decode it. He will not be able to decrypt it without the private key.
Yeah.
So now we will be looking at how to encrypt. Like there are so many different encryption techniques. So that we will discuss now in this lecture, like the main focus for now. So let us start with that. So if we talk about traditional ciphers, we have something like some categories. We will discuss that. Some categories of these traditional ciphers. So we have something called as substitution ciphers and transposition ciphers. So two very important categories of ciphers we have to discuss in detail. Here I will just make a note of it. So we have something known as substitution cipher. And as the name suggests, here the real data which we have, the information, we substitute it, and hence it's the substitution cipher. Substitution cipher. In substitution cipher, replace one symbol in the ciphertext with another. Similarly, we have transposition cipher. In transposition cipher, we don't replace, but we reorder the position. Reorder the position of symbols in the plain text. So it's very interesting that whenever I'm interested in doing cipher like encryption, two options I have. Either I can go for a substitution cipher, wherein I will be replacing symbols with another symbols, or I can go with the transposition cipher, wherein I will be reordering the positions of the symbols in the plain text.
Yes.
Now, both of them we will discuss in detail. So first, let us discuss the substitution cipher in detail.
Okay.
Like different techniques of substitution cipher. As we already saw that in substitution cipher, we replace one symbol with another. Let us look at one basic example to get more clear idea about the substitution cipher, how it works in reality. Let us suppose we are following a substitution mechanism wherein we are replacing the A with the D, T with the Z. We can replace 3 with 7, and we can replace 2 with 6. Like I'm just giving one example. Now the idea is that in the plain text, wherever we will have A, that will be replaced with capital D. In the plain text, wherever we will have T, that will be replaced with Z. And this mapping is very important, because in decryption, reverse mapping we will do. Wherever we will get D, we will convert it to A, like that.
Yeah.
Isn't it?
Yes, sir.
So this we can understand also. Now this substitution cipher, we can classify it into two types. We can classify it into two types. It can be mono-alphabetic ciphers, and they can be poly-alphabetic ciphers. Mono-alphabetic ciphers and poly-alphabetic ciphers. Now, what are these? Let us look at it in some detail. Now, first, let us focus on this mono-alphabetic ciphers. Mono-alphabetic cipher. Mono-alphabetic cipher. What it is? In mono-alphabetic, there is a one-to-one mapping. Like we have the plain text, letters, and we have the cipher text. In mono-alphabetic, there will always be one-to-one mapping. Always. One-to-one. Always. Now, what is this one-to-one mapping? Every letter is assigned a fixed word, and no matter what, it will be replaced with that word only. Like if A is mapped with D, in the plain text, wherever A is there, it will always be mapped with D only. Now, A cannot be mapped with any other number or any other symbol.
Yeah.
Like every symbol will be mapped with another symbol. Not two images are possible. One-to-one. One-to-one means every plain text symbol, there is a unique ciphertext symbol for that. One-to-one.
Yeah.
So that is the mono-alphabetic cipher. Like we can take one example wherein we have a word, we have a plain text, and we have a ciphertext. This plain text which we have, that is the hello. The ciphertext which we have, that is the code. Something like this. Now, why we can say that it can be monoalphabetic? Because L is O. So wherever L is there O is there. And very easily, it is breakable. Like monoalphabetic cipher, it is so worse. Like in terms of security, that if we have a ciphertext, then with some jugaad, like with some efforts, we can break it. We can get back into the original plain text, because this mapping, if I am able to recognize, and I know that every symbol will be mapped with a unique ciphertext symbol,
Yeah.
so it is easily breakable.
Yeah. Yeah. So every word in the plain text maps to one word, the ciphertext. Single word, one to one. Yes.
So this is monoalphabetic. It can be mono, like, but we have another sequence, like plain text, ciphertext. Therein, no such pattern we can see. For example, if we have plain text and we have a ciphertext, we have a plain text something like, once again, hello. But now the ciphertext, it is AB and ZF, and hence it is not a, because now
Yeah.
this LL, it is been assigned different word, like the different
Yeah.
symbols. So it's
Yeah.
the same L,
Polyalphabetics.
the same L alphabet. Once it is N, and another time it is Z. So it is not one-to-one
Yeah.
mapping, and hence
Yeah.
it cannot be mono-alphabetic cipher.
Yeah.
Yeah. Okay, this is very clear to us. And polyalphabetic, it is very clear. Clearly, we can say that in polyalphabetic, the relationship can be one to many. Like one plain text symbol, it can be mapped with multiple ciphertext
Many.
letters.
Yeah. But so every time we use a letter in the plain text, it can be mapped to different letters in the cipher.
Yeah, that is right. Now,
It's easy to understand.
easy to understand. Now we will discuss the next topic in this substitution cipher itself. That is the additive cipher. Additive cipher.
Yes.
This additive cipher is also known as shift cipher or Caesar cipher, and hence it's very important.
Oh, yeah.
Additive cipher, it is also called as shift cipher
Shift cipher.
or the Caesar cipher, and here it is the Julius Caesar, Paulus Caesar.
Yeah. Yeah.
It's right. Now, what is this additive cipher? Let us look at. As the name suggests, here we will be doing some addition. So some kind of a mathematics we will be applying here to transform, like the substitution. So one table I will make to get an idea about its working. Now this table will contain 26 lines, 26 alphabets. So that I will just make a click of here now. I am still struggling to use this. Okay, let me just draw it rough. Let us be fast. Horizontal line, I think. Now let us draw it with a pencil. The plain text is in the small letter A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, and Z. Subtraction. Now this is the small letter. Similarly, we can have a capital letter. A, B, C, D, E, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. And we have some numbers that we call the value. Let us start. We can start from 0, 0, 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, 6, 0, 7, 0, 8, 0, 9, 10. Then we have 11, then 12, then 13, then 14, then 15, then 16, then 17, then 18, then 19, 20, then 21, then 22, then 23, then 24, write 4 properly, and finally 25. Because we are starting from 0, that's why we are getting till 25. Okay. Now the first row, it is the plain text. Like we are assuming that plain text, all the characters of the plain text, they are small letter. And we are assuming that all the letters of the ciphertext, they are capital. Plain text, cipher. And the value. Value is like just any number. Now let us see how this will work, additive cipher. It makes use of some formulas. That is the modular arithmetic that we will discuss modular. And this representation which we have, we call it like Z26. Now let us make one diagram to understand the formulas involved in encryption and decryption using this additive cipher technique.
Yeah. Encryption and decryption using additives.
We have a plain text. Once again, we have a plain text. Idea is very simple.
Okay.
This plain text, it can contain the information in all the small letters. And here also we have the plain text in the receiver end, isn't it?
Yes, sir.
Let us suppose this is the sender. Let us suppose this is the receiver.
Yes.
Now what the sender will do, sender will like convert this plain text. He will encrypt it, and the receiver will decrypt to get back the plain text. Now both of them will make use of a key. We call it like the K. K is the key. It's the private key, isn't it?
Yes, sir.
So both of them will make use of this private key. Okay, this is clear to us until here. Now
Yeah.
exactly what is the encryption and what is the decryption algorithm? That is what is important for us. So in encryption, in encryption, we get cipher text as the result.
Okay.
So C is equal to P plus K mod 26. I can write this with small, we will utilize the space. So capital C, it is the cipher text. So cipher text is equal to plain text plus key
Mod 26.
mod 26. A simple formula. We will do some examples. Then I will get the cipher
Yeah.
text and I will transmit that cipher text to the receiver. And in the receiver, I will get P because decryption. And decryption is
Yeah.
C minus K mod 26.
T minus. Okay.
Isn't it? Now just I have to combine both of this. That is understood. So here C will be there, here P will be. Here also C will be.
The Z means.
So this Z26 now.
Yeah.
Z means a set of integers. I can.
Okay, so 26 integers are there, so Z26.
It's like Z26 representation. It's like Z26 representation.
Okay.
Now here we can see the encryption and here we can see the decryption. In the encryption, plain text is getting converted into the cipher text, and in the decryption, cipher text is getting converted into the plain text. And here we are making use of a formula P plus K mod 26 for encryption and C minus K mod 26 for the decryption.
Like can you tell what is the T and C you have written along with the arrows?
Where?
Plain text and cipher text only.
Yeah. T means plain text, C means cipher text.
Yeah, along with the arrows there you
That.
Okay.
Because encryption algorithm, we are passing the plain text and we are getting cipher text
Getting
as the
the-
output. And that
Okay,
cipher
like
text,
that.
that cipher text we are passing as input to the decryption algorithm.
Yeah, got it.
And decryption algorithm is giving plain text as the output.
Yeah.
Now let us use this to encrypt hello. Now we are doing some very interesting activity. Like one example, like we will simulate for this. You can
Okay.
see, simulate somewhere here. So here, let us suppose, or let me scroll down. So let us suppose the plain text is hello,
Yeah.
and we know that in the plain text everything is small letter. We are
Yes.
making an assumption.
But this is just an assumption. Like actually, we can use capital also.
Yeah, we can use capital. We can use special
But
characters.
for this example,
Yeah. To understand, let us keep
Okay.
it simple. That's and
Okay.
K, which is the key. We are taking 15 to be the key.
okay.
Now in encryption, especially the substitution,
Yeah.
what will happen is every letter will get substituted with the ciphertext, isn't it?
Okay. Yeah, using that formula.
Using that formula. So I will just write it here. This is the plain text. Then I will be doing some encryption on that, and I will be getting ciphertext. Now let us apply that formula. According to that formula,
Yeah.
plain text is like P is HELLO. Encryption formula is P plus K mod 26. So like plain so H, and what is the number for H?
H is 7.
H is 7. H is 7. That's right. So I can write it like this: 07 07 plus P is 15
Yeah. 15.
and mod 26.
Mod 26.
Mod means remainder. Like whatever the sum
Yeah.
is, that we have to divide it by 26, and whatever is the remainder, that will be our answer.
Yeah.
So similarly, we will be doing this for all these characters. E in the table which we made,
Four.
it is 4. So 4 plus 15 mod
19.
26.
Mod 26.
And similarly, we have L. L is 11. 11 plus 15 mod 26. Then once again, 11 plus 15.
11.
Then O. Then 14. From
14,
the table, that's 14.
Yeah. 14.
Now, if we solve it, like the calculation, if we do, we will get something interesting. We will get 22.
22 mod 26.
Yeah.
Yeah.
So
Yeah.
whenever
22. Yeah.
yeah, the number is less than the 26, it will be that number only. So it will be
Yeah.
19.
19. Yeah. This is 26. So 0.
It will be 0, 0.
0.
It will be 0.
And 29 mod 3.
It will be very nice. Now, what we can do, we can assign the characters based on these numbers from the table.
Yeah.
So in the table, if you look at 22, it is
It's
capital
W.
W.
19
19
is
T.
T.
0, 0
A.
is A. 3
T
is
D.
T.
WTAAD.
Yeah, that is hello.
Yeah. Okay, so in
So-
additive cipher, this is the formula, like to obtain ciphertext P plus K mod 26.
Yeah,
And to decrypt P is equal to C minus K mod 26. That's it, right?
that's it. So after
Yeah,
it-
then,
yeah,
Sir, so like the hacker also knows this is the formula of additive cipher. So he can
Yeah.
easily decrypt the ciphertext.
yeah, that is it. He can do it if he knows the formula. And that's why it is not used, but we are learning just to get an idea. Like all these things which we are discussing, it's outdated. But at least,
Oh.
yeah. But we are learning it. Why we are learning it? Just to get an idea how encryption is done. Because
Okay.
we are becoming engineers now. So it
Yeah.
might be that using this we might come across with some innovation.
Yeah, correct.
It might. And tell me one thing. Here,
Yes, sir.
the encryption which we did, is it a one-to-one mapping? Is it a one-to-one
Yeah, it's
mapping?
1-to-1.
And if it's one-to-one, then is it monoalphabetic?
Yeah, it's monoalphabetic.
So we can say very important observation we have made, that this additive cipher, they
It's
are
monoalphabetic.
monoalphabetic. Because the table which we made, there clearly we can see that it is one-to-one mapping,
Yeah,
and hence it is monoalphabetic.
monoalphabetic.
Now we will do the reverse,
Okay.
like decryption.
Decryption. Decryption of WTAAD.
Yeah. So in the decryption, we know that we should have the ciphertext, which we already have.
Yeah.
Then we make use of the decryption algorithm, the formula for the decryption,
And plain text.
and result is the plain text. Now WAAD. Let me stop
Yeah.
it. Space. Isn't it? This is the ciphertext
Yes,
which we
sir.
got. Now
Yeah.
we will apply the decryption and formula.
Yeah.
What is that? C minus K.
C minus K mod 26.
So W is 22. So 22 minus 15. Key will be same for both. That we know. It is a private key cryptography. So the same private key is shared by both. Mod 26. And here we will have 19 minus 15. Mod
26. Then we have 0 minus 15.
0, 0 minus 15. Mod 26. Then once again we have 0, 0 minus 15. Mod 26.
Then we have 3.
In the last we had 3 minus 15 mod 26. Now what we will do, we will perform this operation, and we will get some numbers, like we will get 07,
7.
then 04,
Four.
11 I guess, then once again 11, then 14. And if we convert it into symbols, I will get H, I will get E, I will get L, I will get L, and I will get O.
Last one is 17. Oh, 1 second.
14.
3 minus 4. Oh, sorry, 12. Yeah. 12, then add 26. So 26 minus 12 is 14.
The plain text we got is hello.
Yeah.
So we saw a very interesting example of encryption and decryption, and it is an additive cipher we saw. And we call it the shift cipher also, Caesar cipher also.
Okay.
And why it is called Caesar cipher? There is a story for that. Actually, Julius Caesar, he used additive cipher to communicate with his officers in order to maintain secrecy. Yeah, Julius Caesar at that time, in that era, he made use of this additive cipher to communicate with his officers. And Caesar used the key value of 3. Like in this example, we used 15 as the key. Caesar used 3 as the key for his communication.
Oh, at that time only it was discovered.
At that time it was discovered. Now, though, we discussed the cryptography aspect of this additive cipher.
Yeah.
Wherein we saw how to create a secret code from a plain message, how to convert it into a secret code. Now we will discuss the crypt analysis aspect of this. In crypt analysis aspect, what we will do, the same additive cipher, we will try to break it. Let us try to do this. Because now our goal is that we have to analyze how reliable it is. And for that, crypt analysis we will be doing, isn't it? So I will write crypt analysis of additive ciphers. Crypt analysis, additive ciphers.
Okay.
And it is important. And very interesting learning we are doing that whenever we design any cipher, we have to do the crypt analysis of it.
Oh.
To check its reliability, like how strong it is, how effective it is.
Okay.
Now, one very serious concern we have, like it's very serious concern, that is this additive ciphers, they are vulnerable to certain attacks. Like additive ciphers are vulnerable. Ciphertext only attack. And I hope you remember this, we studied.
Yeah. Ciphertext.
Ciphertext. What it is? Ciphertext only attacks.
Just that the hacker gets the ciphertext from the insecure channel and he analyzes it and he tries to produce the plain text from it.
Very nice, very nice. So the idea is that if in this additive ciphers, if the attacker he gets access to the ciphertext, then he can use the brute force, because the key, we know key can be any number. Like here it is like 1 to 26, for example. So very easily he can apply this brute force.
Oh, here the key should be in the range 0 to 26.
Yeah.
Is it? It can be anything, 100
it can be anything for sure. But still then also, it will be a number only now. For a program, it is just a matter of milliseconds. For a computer system, it's just a matter of milliseconds to check millions of numbers.
Okay.
Like very easily, we can check all the numbers 1, 2, 3, 4, 5, 6, 7. So with brute force, it is possible to break the additive ciphers.
Okay.
The additive cipher which we are discussing in this example, it is even worse. It is even worse. Worse in that sense that the key domain is just 26 characters. Like we are assuming that there will be only 26 possible keys.
Okay. 26 keys.
And in this 26 keys, or we will make it 25 keys, because 0 is useless.
Oh, so like there is a range, right? 0 to 25.
And so key
we can't use outside that.
Yeah, but the possible keys, that is 25, because 0 is useless.
Yeah.
0 we don't. Possible keys is 25 keys, because 0 is useless. The key with value 0 is used. Now tell me, with brute force attack, very easily we can check all these 25 keys, isn't it? Now let us do the crypt analysis. With a real world example. And it is very interesting discussion. Now we are getting a feel of this chapter.
Yeah.
Let us suppose we have a scenario wherein cipher text. Like, let me first write heading, that is like example. Otherwise, it will be confusing. So now we will discuss one example. Let us suppose cipher text, that is the capital C. Let it be something like this: U V A C L Y F Z L J B Y L. So it is a very weird, because cipher text is always weird. Just imagine that we were able to steal a cipher text from an unsecure channel or insecure channel, communication channel, and we found something like this, a very weird cipher text we got. Now our goal is to break it, decode the plain text, or decrypt this without knowing the key, because key we don't know, we only know the ciphertext. So we will apply the brute force technique, and let's see how we will do that. So we know that in brute force technique, we will apply different possible values of the key. So when the key will be 1, when the key will be 2, when the key will be 3, when the key will be 4, like that. Or in order to make it bit simple, I can write it like this: E, K, and plain text. For different values of K, I will get different values of P, the plain text. And how I will get it? Decryption algorithm, formula.
Like the formula.
If the key is 1, 2, 3, 4, 5, 6, 7, and so on. The plain text which we will get, the decryption formula, if you remember, C minus K mod 26.
C minus K mod 20.
That formula, if I apply, I will write it somewhere so that you'll be aware of it.
Plain text.
C minus K mod 26. This is the formula. And we will get the plain text. So now I am just writing the plain text directly. After the computation, we will get plain text for here. T U Z B K X T Y T I A X T. Then we have something weird: H T Y A J W D X J H Z W J. Okay. And if we are getting weird plain text, then we can understand that, okay, this is not the key we are looking for. So definitely there will be one key which will give us a relevant plain text, an understandable plain text. And that is the eureka moment for us. Similarly, we will get some weird text.
What?
Here we will get some weird text. Some weird text. But for 7, we will get something magical. For 7, we will get something like this. That is not very secure. And this is what is something relevant, understandable to us. And we were able to crack the code. Using the crypt analysis. Using the crypt analysis, we were able to crack the additive cipher, the Caesar cipher. We were able to crack. And hence, it is so easy for the computer. Like 25 keys, it can check it in milliseconds. And all the plain text we will get, we just have to go through all the plain text. Wherever we are getting something relevant, something understandable, then we know that, okay, this is the key. And every time, now from that insecure channel, whatever ciphertext we are stealing, we can use this key to decode all the information. And that system got compromised. So this is the additive cipher prone to brute force attack.
Okay.
Now, additive ciphers can also undergo statistical attacks.
Okay.
Let us discuss that. That is the ciphertext only attack using statistical attacks. Ciphertext only statistical attacks. Let us look at one example. We have already seen that in statistical attacks, we make use the concept of frequency. Frequency of occurrence. Frequency of occurrence of characters. We can make use of it.
E is the most occurring.
So we have a table. I will draw a rough of it. Very fast I will do it. For letter E, in the bracket I am writing the frequency. That is 12.7. Capital T, it is 9. For capital A, it is 8.2. For capital O, it is 7.5. And for capital I, it is 7. And for capital N, it is 6.7. Decreasing. Capital S, it is 6.3. Then H, the frequency is 6.1. Then R, it is 6.0. Then capital D, it is 4.3. Capital L, it is 4.0. Capital C, it is 2.8.
Okay.
Then capital U also 2.8. So the frequency is so low. And capital M, it is just 2.4. And capital W is just 2.3. It's decreasing. Then F, it is 2.2. Capital G, it is 2.0. Capital Y also 2.0. Capital P, 1.9. Capital B, 1.5. So B has a very small frequency. B is just 1.0.
Okay.
Then K, it is just 0.08. It is very less. Then J, it is 0.02. Q, it is 0.01. X, it is 0.01. And capital Z, it is 0.0. This is the frequency of. Now the idea is that now, like frequency of occurrence of one character,
Yeah.
that many a times only that is not sufficient. So what we do,
Okay.
we take two characters together and calculate its frequency, and we call it like diagram. Then we take three characters and calculate its
Okay.
frequency, that we call trigram. I will write it. So we make use of diagram and trigram, isn't it?
Yes, sir. Right.
So this diagram is the 2-letter group and trigram is the 3-letter group. The 3-letter group. I think we are discussing the cyber security, and I think I can see one red laser.
Then how do I get out of this?
Okay, you
I'm
are
trying from that time.
that I was thinking from where this red laser we got.
No, like I was scrolling up by mistake. I clicked on that laser. So I'm not able to quit only.
That's fine. Let it be. Now we will do one thing. Now we will look at one example wherein we will be like we were able to steal any ciphertext, and we will make use of this. Okay, so don't write anything here.
No, sir.
Everything was selected. Okay. Let us focus here. Let us focus.
Yeah, the
Like one-
laser also got.
Yeah. One very interesting example we will discuss. One very interesting example wherein we were able to get access to a very weird ciphertext. Because ciphertext, we know it's always weird. So let us look at that weird ciphertext which we got into access. X L I L S Y W I M W R S A J S V W E P I J S V J S Y V Q M P P M S R H S P P E V W M X M W A S V X, then one hyphen, then L Q S V I L Y. So a very weird ciphertext we are writing. Last few letters we have to write. BBCF IJSV. So it is the encrypted ciphertext, and we will break it very soon.
Okay.
IXLI WI PPI BVIG IMZI WQS VIS JJI BW. So this is the ciphertext. Now let us break it. So some steps we will follow. Let us see that. Now what we will do, we will first count the frequencies, like occurrence, number of occurrence.
Yeah.
And when we try to do that, we will see that I is occurring 14 times. In the ciphertext, I is occurring 14 times. B is occurring 13 times. S is occurring 12 times, and so on. So whenever we are doing the statistical attack, whatever ciphertext we have, the first step is to calculate the frequencies of each symbol. Like every symbol, how many times it is repeating or how many times it is occurring. That frequency count we have to calculate.
Yeah.
Now, the most common character,
Is E.
no, like in the ciphertext, most common character, that is the I.
Oh, is I.
Most common character should be mapped to E.
Yeah.
Should be mapped to small e. It implies that, so it is understood, okay, like most common character, that is the I.
Oh.
I should be mapped to E. So wherever I is there in the ciphertext, that I we can replace it with small e in the plain text. Should be mapped to e in plain text. Now the next point. And if that e, so we can take e as 4, because if we start with a is equal to 0, then e will be 4. Now with this, all this initial finding, we can break this.
Yeah, but E is the how is E related to the key?
Yeah. Yeah, that is a good question. So in statistical attacks, it is related. Like in brute force, it is not related, because in brute force, to every key we have to check. But here we make an educated guess for the key. Like, see, we already saw that in brute force, all the key we guess. But in statistical attack, we don't test for all the keys. We make an educated guess, and here the educated guess is key is 4. In statistical text, we always start with key is equal to 4. We will make an educated guess. Then we will check the next most occurring character and the numerical value of that in the table.
Oh, very cool.
So that the key we take in the second attempt. In the third attempt, the third character with the most frequency. So the number for that character, that will be the key in the third attempt. In this way, we make educated guess for the key and not blind guess. Now with this key as 4, and with this one observation that okay, I can be mapped to E, then I will be able to like recognize a pattern using which I can say that okay, this can be something like this. The house is now for sale. The house is now for sale for $4 million. Like we will get back to this how we got it. We'll get back to this. It is worth more. It is worth more. Hurry before the seller receives more offers. Okay. Now see what we did. Let us just try to understand.
Okay.
Wherever I was there, we try to replace it with E.
Yes, sir.
And I was there so many places. And similarly, V, wherever V was there, the second most occurring character in the table, that is T.
T, yeah.
So V we converted it to T. Similarly, S we converted it into A, something like that. And we were able to decrypt it.
And key we always take off the most, like first E's key.
Yeah.
Like E's
The
and key we take off the E, like E's letter, that is 4. And if not, then T's numerical, that is something that like that.
Like that.
Okay.
So this was additive ciphers. Yeah. Now today we will discuss multiplicative ciphers. That is the agenda for today. Like multiplicative ciphers, then affine ciphers also we will try to complete. Let us see how far we can go. So first let us focus on multiplicative ciphers. So as the name suggests, here in the encryption and decryption, we will be using this multiplication and division. So the formula will be different. So exactly, let us look at multiplicative ciphers, how it works. So in multiplicative cipher, encryption, it involves the multiplication with the key. So the encryption formula will be, in encryption, we get ciphertext. We make use of the plain text. So here, plain text, we will be multiplying it with the key. Like I will use the dot for multiplication. Dot means multiplication. And K is the key. And mod 26. So this is the formula for encryption in multiplicative ciphers. And for decryption, we have, in the decryption, we get plain text as the result, and we make use of the ciphertext. So we multiply the ciphertext with inverse of K, like 1 by K. So now it is very clear to us that okay, multiplicative ciphers in encryption, whatever plain text we have, we multiply it with the key, private key, that is the K, and we do the mod 26, and we get the cipher text symbol. And for decryption, whatever ciphertext symbol we have, we multiply it with the inverse of the key, K inverse, and we do the mod 26, and we get the plain text symbol. Now, one very important discussion we should make in multiplicative ciphers, the C comma P, like the cipher text symbols and plain text symbols, they belong to the the set capital Z26. It means set of alphabets like capital A to capital Z, small a to small z. We have seen that, or we have assumed that plain text always contain alphabets in small letters and ciphertext always contain alphabets in capital letters. This we have assumed. But very interesting observation, the key here, this key belongs to the set Z26 star. And this Z26 star is the set of odd numbers. Set of odd numbers. So I can say that the key domain is, I can write it here. In multiplicative ciphers, the key domain, like the set of possible values which the key can take, that is the set of odd numbers from 1 to 26. Set of odd numbers from 1 to 26. 1, 3, 5, 7, 9, 11, 13, 15, 17, 19, 21, 23, 25. So in total we have 12. 1, 2, 6, 7, 9, 10, 11, 12, 13, 13 numbers. Now let us look at one example. Like we will do the encryption, decryption, and cryptanalysis using this multiplicative ciphers. So let us look at one example of it. Let us suppose I have a message that is the hello. So plain text is hello, for example. And the key which we are using, the key, let us suppose it is 7. Because always remember, in the multiplicative ciphers, we can only use odd numbers as the key. So the key can be any value like 1, 3, 5, 7 up to 25. Key cannot be 2, key cannot be any even number. Okay, it's very important. Now we have to make use of the table. Let us try to copy that table which we created. The mapping of numbers and the symbols. This is a very important table. Let me try to copy so that we can use it once again in this question. So whenever you are solving a problem, you make that table once and you can refer it multiple times. So this table we have to make use of. So we have this table. Now let us solve this problem. So now what we are trying to do is that we have a plain text that is hello. We will be encrypting it using the multiplicative cipher technique. And let us see how we will do that. So the idea is very simple. I have a plain text, that is the P. I will be using a encryption formula that we know. So the encryption formula is C is equals to P into K mod 26 for multiplicative ciphers. So we have the plain text, we have the encryption formula, and then what we have the ciphertext. Like we will get the ciphertext as a result. And this ciphertext we represent it C. Now let us do this for hello. So in the given scenario, our plain text is H, E, L, L. The encryption will be the formula if we apply, that is H. And what is H? H is from the table, it is 7. So we can say that 0, 7, and here key is 7. Key we have taken 7 now in the example. So 7 into 7 mod 26. Similarly, E is 4. So 4 into 7 mod 26. Then we have L, that is 11. 11 into 7 mod 26. Then once again we have 11. 11 into 7 mod 26. Then we have O. O is 14. So 14 into 7 mod 26. Now when we solve this, 7 sevens are 49. So 49 mod 26 when we will do, we will get 23. And in the table we can see that 23 is X. Similarly 28 mod 26 is 2. And 2 is the capital C. Then 77 mod 26, that is 25. And this 25 is Z. Then 77, once again 25. That is, and in the last we have 14 into 7 mod 26, that is 20. And 20 is the capital U. So we got the ciphertext. After this operation, I can say that ciphertext C is equals to the capital C. Ciphertext is the capital C. Capital C is equal to capital X, C, Z, Z. If hello is the plain text, this is the ciphertext for that. Now, in a similar manner, we can decrypt it. So let us decrypt also. In decryption, we will be having ciphertext with us. So we will be starting with the ciphertext. That ciphertext is the capital C, and we will be applying a decryption algorithm. Here the decryption formula is a bit different. Here we have to multiply the cipher text with the inverse of the key. So P is equals to C dot K inverse mod 26. And after this operation, we will get plain text as the result. In decryption, we get plain text as the result, because decryption converts the cipher text into the plain text. Now let us try this. So we have X, C, Z, Z, capital U. And when I will apply the decryption, it will be something like this, wherein I will be multiplying the capital X with K inverse. So K inverse will be 1 by 7. Because K is 7, K inverse will be 1 by 7. So what is capital X? Let me open the table. So from the table, you can say that capital X is 23. 23 into 1 by 7 mod 26. Okay. Then capital C, we have 2 into 1 by 7 mod 26. Then we have capital Z, 25 into 1 by 7 mod 26. Then once again we have 25 into 1 by 7 mod 26. Then we have capital U, that is 20 into 1 by 7 mod 26. Okay. Now the question is how to solve this, because 1 by 7 is there now. Are you aware of solving this? How to solve this? Hello. Yeah, please unmute and tell, are you aware of this? So when we will solve this, we will get something like this. We will get 0.7, then we will get 0.4, then we will get 11, then once again we will get 11, and once again then we will get 14. And this 0.7 is H, E, L.
How did we get that?
L. Yeah, that is what I am asking. Are you aware of this? Okay, we will discuss. So what I will do now, like there is a concept of modular arithmetic in discrete mathematics. I think you might have studied the modular arithmetic. What I will do, we will discuss that separately. Like half an hour, we will have a small session wherein I will tell you some important formulas of modular arithmetic.
Okay.
Therein we will discuss this technique, how to solve this. Okay.
Okay.
Now you just assume that, okay, we know that technique, we solved it, we got this.
Okay.
Yep. And that modular arithmetic, it plays a very important role in cryptography, and you will see it a lot in different scenarios. So this was multiplicative ciphers. So we saw that, okay, multiplicative ciphers. Now if we look at the crypt analysis, like how reliable it is, can we rely on multiplicative ciphers? So let us discuss that. Let us discuss the crypt analysis of multiplicative ciphers.
Okay.
Yeah. Crypt analysis of multiplicative ciphers. So we already saw that the key domain means set of the keys which we can take in multiplicative cipher. That is very small. If you remember, we just discussed.
Yes, it's like only 25, right?
No, key domain is only set of odd numbers from 1 to 25. It is 13.
Key domain of
multiplicative ciphers.
Yeah. Oh, multiplicative. Yeah. That additive, it's I think 25. Multiplicative, 13.
Yeah, multiplicative. We saw now in multiplicative ciphers, the key can take only the odd numbers, and so small domain it is. So it is so easily, it is like highly vulnerable to brute force attack, because we just have to make a guess of only these many keys. Like first I will take k is equal to 1, then k is equal to 3, then 5, and I will decrypt it. And once I get a relevant message, a message which I can understand, then I can say that, okay, this is the key. So it is prone to brute force attack, or it is vulnerable to brute force attack because of very less domain size. Easily we can apply the brute force attack. So I can say that multiplicative ciphers are vulnerable brute force attack. And also, see, if I talk about statistical attacks, so in the statistical attacks, we try to do the statistical analysis wherein the frequency count plays a very important role. Here, the frequency is not hidden. Why it is not hidden? Because if Z is repeating 2 times, L is also repeating 2 times. Like so, the frequency information very easily we can decode. I hope you are getting what I am trying to say. In the plain text, if I have a symbol which is repeating 100 times, then in the cipher text that symbol will repeat 100 times, but with a different label, because we are mapping now. L is mapped to capital Z, so capital Z will repeat 100 times. So the distribution, statistical distribution is same. Like in multiplicative ciphers, the statistical distribution is preserved, and hence it is prone to statistical attack. Because when I analyze the cipher text, I can say that oh, capital Z is occurring 100 times. It means the symbol corresponding to capital Z in the plain text, it is occurring 100 times, and I can like plan some statistical attack to get to the key and decode the plain text. It is possible. So multiplicative cipher, it is vulnerable to brute force attack, and also it is vulnerable to statistical attacks. So both the technique which we saw, the additive ciphers and the multiplicative ciphers, they are not at all secure. Definitely they are solving the purpose. They are solving the purpose of converting the plain text into some code, so some hidden text or some ciphered text that it is doing. But that cipher text is not secure because we can break it. It can be broken because the domain of the key, it is very small, like just 25 or 30. So very easily one can apply the brute force attack to decipher, and hence the confidentiality of the system will be compromised, integrity of the system will be compromised. So these are not reliable techniques. Now we will discuss one more encryption technique, and that is affine ciphers. So now we are starting with a new technique for encryption. So we have something that is affine ciphers. Affine cipher. Now let us see what it is. So affine cipher, basically it is a combination of both multiplicative and additive, and it uses a pair of key. So affine cipher, you can say that it's a combination of multiplicative and additive. So two keys are used. So multiplicative cipher plus additive cipher, combination. With multiplicative cipher, we make use of a different key that we can call it K1, and with additive cipher, we make a use of a different key that we can call it K2. So now let us look at how encryption and decryption looks in affine cipher. So in affine cipher, we have encryption and we have decryption. So the encryption and decryption. So the formula for encryption is something like this for the affine cipher. That is, we can say that capital C, that is the cipher text, is equal to first multiplicative plain text into K1, then additive plus K2, mod 26. And in the decryption, we will get plain text as the answer, and that will be first subtraction, that is C minus K2. Then I have to multiply it with K1 inverse, mod 26. So this is the formula for encryption and decryption in affine cipher. So in affine cipher, it is a combination of multiplicative cipher and additive cipher. Two keys are used, K1 and K2. So first in encryption, first we do the multiplication. So we multiply the plain text with the K1 key, and then we will add the result with the K2 key and do the mod 26 to get the ciphertext symbol. And in decryption, whatever ciphertext symbol I have, first I subtract the K2, and then the result I will get, I will multiply it with K1 inverse, and then I do the mod 26. Then I will get the corresponding plain text symbol for that ciphertext symbol. So this formula is very clear to us. Now let us draw the architecture of it, because that is something important. So now the idea is that the plain text, we will pass it here, and the plain text we will get from. So I will write it down. So we have a plain text. In the encryption, the plain text, first we do the multiplication. So the formula will be something like this. We will get capital T is equal to plain text that I am calling as P into key. I can use dot K1 key is the K1. It will make use of K1, and whatever result I will get, I will do the mod 26. Now whatever T I got, I will add K2 with it, and I will get ciphertext. So C is equals to T plus K2 mod 26. So here I will pass K2. I will get the text, ciphertext, that I will transport it to the destination receiver, and receiver will receive it, isn't it? So something like this. So here we have the sender, here we have the receiver. Here is taking place, that is the encryption, and here what is taking place, that is the decryption. And whatever ciphertext capital C we are sending, it will be receiving that, and it will be doing the decryption. In the decryption, first we will be subtracting. So first we will get T is equal to whatever ciphertext I got, that minus K2. So C minus K2 mod 26. This is also using the key K2. Then the T will be transferred to the next step, wherein we will calculate the capital P, that is a plain text. So what is capital P? Whatever T we got, we multiply it with K1 inverse. T dot K1 inverse, and do the mod 26. Then we do the mod 26, and this is the K1, and we will get P as the plain text we will get once again. So this is how the affine cipher works. This is the mechanism through which, and hence we can see this affine cipher. It is a combination of both multiplicative cipher and additive cipher. So both the concepts are applied here, one at a time. Now let us move forward. Now let us look at one example. Let us look at one example using, or I can say that encrypt hello, encrypt message hello, or I can say that encrypt and decrypt, both types. Encrypt and decrypt message hello using affine cipher. Take 7,2 as the key pair. So let us do this. So first let us copy that table. Because that table we will be needing this.
Yeah, easy.
So let us copy this. Let us paste it. Now let us do it. So we will start in the encryption. We will start with the plain text. Whatever the plain text we have, we will encrypt it, and we will use a formula. What is encryption? In encryption, we will get ciphertext. So first we multiply P into K1. Then whatever result we will get, we will add it. Then we will take the mod 26.
Mod 26.
Then we will get the ciphertext. So the plain text which we have, that is the hello.
Yeah.
And when we encrypt, so let us encrypt, we will apply this formula. Now the K1 is 7 and K2 is 2. So it will become H is in the table, it is 0, 7. So 0, 7 into K1, that is 7, plus 2 mod 26.
14.
Similarly, when I will do this, E is 4. 0, 4 into 7 plus 2.
34.
Mod 26. Yeah. Then we have L, that is 11. 11 into 7 plus 2, mod 26. Then once again we have 11 into 7 plus 2, mod 26. Then finally we have O. O is the 14. So 14 into 7 plus 2, mod 26. Now let us get the ciphertext. So 7 7s are 14 and 51 mod 26. That will be 25.
25. Z.
Then what we will get?
Then 4. 4 is E. 17.
Then we will get 1.
1. B.
Then we will get 1 once again. Then we will get 22.
Yeah, 22.
That is W. So ciphertext we got. So I can say that ciphertext C is equal to Z E B B. Z E B B W. Isn't it?
Yeah.
Okay. Now we will decrypt. In decryption, we have the ciphertext. We apply the decryption as well. That is plain text is equal to C minus K2 into K1 inverse mod 26. Then we will get the plain text as the result. Now let us see Z E B B W. Isn't it?
Yeah.
It will become Z. So Z is 25.
25.
25 minus 2
2.
into 7 inverse mod 26. Here I can write the key 7 comma. So K1 is 7, K2 is now capital E, it is 4. So 4 minus 2 into 7 inverse mod 26. Then we have B, that is 0, 1 minus 2 into 7 inverse mod 26. Then once again we have 0, 1 minus 2 into 7 inverse mod 26. And finally capital W is 22. 22 minus 2 into 7 inverse mod 26. And when I will do this, I will get 7, that is small h. Then I will get 4, that is E. Then I will get 11, that is L. Then once again I will get 11, that is L. And then I will get 14, that is O. So this is what I got.
Yeah.
This is the plain text.
Yeah, got it.
So plain text P is equal to HCLLO. So using this affine cipher technique, we encrypted and decrypted a message with a particular key.
Yeah.
Now in this affine cipher, one more thing we can discuss. Like in the concept itself, we can discuss it.
Okay.
That we can discuss it. In affine cipher, we know that we use two keys. And if I make one key, like I will tell you, when K1 is equal to 1, when K1 is 1, then what will happen?
When K1 is 1. 1 second.
Like in the encryption decryption formula, just
Yeah.
put K1 is equal to 1 and see what will happen.
It's just like plain text plus K2 mod 26. So no effect of K1.
So it will become similar to which formula?
It will become similar to, I think, multiplicative.
Why?
Because in that also it's plain text into key mod 26.
Yes, so into term is getting vanished now. When
Huh?
K1 is 1, when K1 is 1, this
Yeah.
into term will vanish. It will just become P plus K, P plus K2, then C minus K2. And that is the additive.
Yeah, additive. I got confused. Yeah, sorry.
It is additive. So the idea is that in the affine cipher, if we take one of the key, like the first key as 1, then it will become additive cipher.
And if K2 is 0, then it's multiplicative cipher.
That's right. Because when K2 will become 0, then it will become multiplicative cipher. That is right.
K2, yes. Okay.
Now we will do the crypt analysis of affine cipher. It is very interesting. Crypt analysis of affine cipher. Just a minute. So crypt analysis.
Sir, can I go to washroom?
Yeah. Let me know when you are back. Like when you will be back, just let me know, then we will back.
Yes.
Crypt analysis.
Yes, sir. Oh, time.
Okay, so let's continue.
Yes, sir.
And so let us do the crypt analysis of affine cipher.
Okay.
So it's interesting. So first let us look at in the terms of brute force. So whenever we are discussing the brute force, we have to check the size of the domain, key domain.
Okay.
So size of key domain for the affine cipher. So let us calculate it. Okay.
Yeah.
We know that affine cipher is a combination of K1 and K2.
Yeah. Additive and multiplicative.
Yeah, that is right. K1, comma K2. Now this K1 is the additive. No, K1 is the multiplicative and K2 is the additive.
Yeah.
We know that for multiplicative, we have like 12 options. Like see, 1 we are not taking. Like we know, including 1, it is 13 options available for the key, but 1 we are not taking because no point of multiplying any number with 1. We will get that number itself. So 1 we are ignoring. So in total, we have 12 options for K1, and for K2, we have 25 options. Like excluding that number, all other numbers can be the key.
Oh.
Or we can go with 26. We can include that number also as the key in total. So if it is so total the domain size will be 312, which is still very less. So the idea is that in affine cipher, in total 312 possible keys we can use, like K1, K2 we can use. In total we have 312, and these 312 we can easily duplicate, like we can test, because 312 is a very small number for brute force. So we have proved that affine cipher is vulnerable to
Brute force.
cipher brute force attack.
Yeah, it's vulnerable to brute force attack. Brute force
Yeah,
attack.
vulnerable to brute force attack, isn't it?
Yeah,
And what you tell about the statistical attack, is it vulnerable to statistical attack, affine cipher?
yeah. Fine, sir. Yeah, it's
Why?
because like it is a combination of additive and multiplicative, and both are like vulnerable to statistical attack. So I just guessed that it is also.
Okay, okay, nice. So your answer is right. And, we can look at it here now. Then we
Yeah.
have L, we have a fixed B. It's a one-to-one mapping. So whenever we will get L, we will get B. So in the plain text, if the frequency of L is 100, like 100 times the L is repeating, in the cipher text also the B will repeat 100 times.
Yeah.
So the frequency is preserved. And whenever this frequency is preserved, then the cipher text is vulnerable to statistical attack.
Yeah. Because we can take that as E, right?
Yeah.
Most used word E, then second most used word T, like that. Yeah.
Like that. Yeah. Like,
Frequency.
whatever is the statistical technique. Yeah. Tell.
No, that only. Its frequency is preserved.
Frequency is preserved. That is the idea. So we can say that frequency of the symbol is preserved. Frequency of symbols preserved. Because of which it is
Vulnerable to statistics.
So
every monoalphabetic cipher is automatically vulnerable to statistical attack.
Yeah, very nice. That's the right answer. Because one-to-one mapping is there.
Yeah.
So frequency will always be preserved. And we can use statistical attack.
So we have to use polyalphabetic. These are all like old, I think, ciphers.
Yeah, old cipher. We are learning this to just get an idea, to just get a feel of like how we do the cipher.
Okay.
Now we will do one very interesting experiment, or you can say that a use case, wherein we will be using the chosen plain text attack for the cryptanalysis of affine cipher. And we will get one example of this chosen plain text attack, like how it is being done. Chosen plain text attack. So it's very interesting. In the chosen plain text attack, we know that the attacker, he chooses a plain text and somehow he gets access to the system of the sender.
Yeah.
So let us suppose the attacker gets into the computer of the sender, and the chosen plain text, let us suppose it is ET. Like he had very less time. Like attacker somehow he got access to the system of the sender. He had very less time, so he was only able to type 2 letters. That is ET. So ET is the chosen plain text, and in that machine, in the system of the sender, he uses 2 algorithms, because ultimately his goal is to get the key. And both the algorithm will use the same secret key. So he makes use of 2 encryption algorithms, algorithm 1 and algorithm 2. For this chosen plain text, we get the cipher text as WC and WF. And where we are doing all this activity, sender system. Attacker getting access into the sender system, encrypting over there and encrypting chosen plain text. Now let us use the affine cipher technique.
Sir.
Yeah.
Can you once again like quick explain this? Chosen plain text is ET. He puts it in the sender's device. Then
and the in the sender device, 2 algorithms are used. Like first he uses any algorithm 1, and that algorithm encrypts it with a technique, and we get a cipher text that is WC.
Yeah.
And once again, the chosen plain text, it is been encrypted with any other algorithm, that is algorithm 2, and then we get WF.
Okay.
The idea is that both the algorithms, they make use of the same private key.
Yeah.
And what is the goal of the attacker? The goal of the attacker, the objective of the attacker is to steal that private key, or to get to know that private key. Because if that private key is known, then
Yeah.
I can decrypt all the messages, all the ciphertext I can decrypt.
Yeah.
Okay.
Okay. So it goes through this algorithm and so it decrypts it and gives the result WC and WF, right?
Now, only using this information, like see, attacker, he was able to get into the system. He was able to get this information that okay, with for ET, I got WC as the ciphertext, and for ET, I also got WF as the ciphertext. Now, using this information, we will identify the key, and how we will do that, that we will see.
Yeah. That's what my doubt. How to identify the key using this ciphertext. Yeah, that we will see. Okay.
Let us try that. Just 1 minute.
Yeah.
So we will test for both one by one. First, let us test for WC. Then we will test for WF. Once we get WC as the ciphertext, we will work around for that. Then we got WF as the ciphertext. We will work around for that. How we will work around? Let us see. The idea is that we saw that for E we got W here, and for T it got converted into C. So we can say that E04, we can say that 04 got encrypted into W, that is 22, and 19 it got encrypted into 2. Any doubt in this?
No.
This is just the numbers, like we convert the symbols into the numbers using that table.
Yeah, but
Now we will apply the formula of affine cipher
of decryption.
of encryption.
Encryption. Oh.
Because he encrypted the plain text ET into WC, and in that encryption formula key is used that we don't know, so that we will assume K1 and K2.
Yeah, we can also do like this, right? WC will
Yeah.
take as the ciphertext, ET as the plain text. So W gets converted to E, C gets converted to T, and then use decryption formula. I was telling like that.
No, that is, yeah, but you are telling it okay, but it is not.
But concept wise, this is correct. What you
Concept wise, this is.
Yeah.
So I am just applying the formula. So formula says that whatever the plain text I have, that is the 04 for the first scenario, or I can write it here is to be more precise. Let me write it here is. So I can write it 04 into K1 plus K2 mod 26. It is equal to 22 because result we know, because this result should be equal to 22. That so that I can write it, and this I can write it 90 into K1 plus K2 mod 26. It is equal to, now here I will use some mathematics, so for simplifying this, and how I will do that, just look at it. See, what I can do is I know that K1 K2, if I break it into a matrix, if I multiply it with 4 1 19 1, I will get the same, like 4K1, okay, 4K1 plus K2, something like that. Just 1 minute.
Sir, it should be 4, 19 and 1, 1, I think.
Okay, so let me correct it. Let me make a row matrix.
Yeah.
Actually, yeah, we have to convert it that way that we can write it exactly the way we have. Now is it right? Now we will get 4K1 plus K2. That is what we want.
Yeah, correct.
And 19K1 plus K2. That is what.
Yeah.
So this is right. And in matrix, it is very interesting that if the matrix is getting operated with the same operation,
yeah,
we can eliminate that operation.
Oh.
Like if mod 26 is there, the reverse of mod 26, if I do it, it will get nullified. Then I can get rid of this.
Okay.
And I will get something like 22 and 2 as the result. Now I want to calculate K1, K2.
How did you get 22 and 2?
No, because see, this is the formula, na? This is the formula for the ciphertext, and we know the ciphertext, that is the W. W is 22. Like affine cipher, what it says that when I perform this operation, I should get ciphertext.
Yeah.
And ciphertext, I already know that it is W.
Yeah. Oh.
So that's why I can write 22.
Okay.
Because
but in terms of that multiplication, Like I was like how
So,
to
so,
do
so this is the result now. So
result.
if see what is the first equation? First equation is 4k1 plus k2 is equal to 22, and this is
Just
what we will
to
get.
equations we
Yeah.
can
So
uh,
these two equations we can convert it into this matrix.
we can use a elimination method.
Now we have to solve this. So we can say that k1 k2.
Two equations, two variables. That's it.
Yeah, it will be 4 1 19 1 inverse. So we have to calculate the inverse of this matrix and multiply it with 22 and 2. We can do like this now. We can take 4 1 19 1 to the right hand side. So it will become inverse.
Oh yeah. Oh, I was thinking K1, K2, the left hand side. This
Mhm.
left hand side hand there, right? I will tell. This left hand side is there, right?
Mhm.
I was thinking the answer of this is equal to right hand side, but this was just we are copying this down here.
Yeah, that is
I was thinking K1 and K2 are 22 and 2. That's what I was.
no. We are copying
Yeah,
it down.
that's why I was confused. Now I got it.
Now you got it, and the inverse also you got it.
Yeah.
Okay, nice. Now we will just do the inverse. 19, 7, 3, 24. Like inverse of a matrix we do, we will get this. If you want, you can revise it, how to do the inverse. Like so many methods are there. Adjoint is there, determinant is there, like formula is there. So all that we can get it. So we will get something like this. Or we can write it in the column form, because final answer, if its order is 2 cross 2, 2 cross 1. It will be like 2 cross 1 is 2 row 1 column. I can write it up. It's fine. Order will not matter. Like, yeah, I'm okay with that. Okay, this result will give me two numbers, and the first one will be the K1 and second one will be the K2. And after simplification, you will get K1 as 16 and K2 as 10. Any doubt till here? Now, very important observation you have to make. See, K1 is the key of multiplicative cipher or additive cipher. K1 is the key of multiplicative cipher, no?
K1 is multiplicative, yeah. K2 is additive.
Additive. And we have seen that multiplicative ciphers can have key that is only odd numbers. We
Yeah,
have
yeah. Multiplicative odd, yeah.
only odd numbers they can have the key as like key value can be only odd numbers. But here we are getting key value as even number. Like K1 cannot be even.
Yeah.
According to the affine cipher rules
Yeah.
or multiplicative cipher rule. So it is violating that. It means that this cannot be the right scenario.
Then WF.
Then we have to go to WF.
So like algorithm 1 is wrong.
Yeah, algorithm one, whatever it is giving us, it is not the affine cipher algorithm, and hence we will not be able to determine the key, that whatever key we have determined, that is not the right key. 16 and 10, it is not correct. Now algorithm 2, what it gave us, so for E it gave us W, and for T it gave us capital F. So we can say 04 is 22 and 19 is 05. Now we can do the same formula we can apply. Like whatever plain text we have, we will multiply it with K1 and add it with K2, do the mod, and we will get, so we should get 22 as the answer.
Then what is the formula of calculating inverse adjoint?
That please you refer.
Okay.
You can Google it very easily, you can get it.
Okay.
That you can get. Here 19 into K1 plus K2 mod 26. It will be 5, isn't it?
Yeah.
So this is the formula which you should follow.
Yeah.
So once again, we can convert it into this equation, wherein I can say that K1, K2, it should be 0, 4, 1, 19, like multi K1, K2 into this into this is equal to 22 and 5. Similarly, I can write K1, K2 is equal to 0, 4, 1, 19, 1 inverse 22, 0, 5. Now, after simplifying this, like the basic mathematics, I will not do. Like you can try it out. Final answer I will write. It is, you will get K1 as 11 and K2 as 4. That is possible. So attacker was able to get the key, and K1 is an odd number. So there is a possibility that, okay, this is right or this can be right. Now to further verify, okay, whatever key I have predicted, that is right or wrong, what attacker will do? Attacker will steal some ciphertext
And then verify.
and then verify whether he is getting a
Meaningful.
meaningful plain text or not. So let us suppose the attacker now got some ciphertext like this. So PWUFF,
Sorry, sir.
OGW, CHF, DWI, WEJ, OUU, capital N, JOR, SM, DWRH, BCM, WJU, PVCCG. So this is the ciphertext. Okay. Now we can convert this ciphertext into plain text using the decryption. We know the key. So here the key K1 is 11 and K2 is 4.
Cryptanalysis.
Cryptanalysis. And the formula plain text is equals to C minus K2 into K1 inverse mod 26. This is the decryption formula. Now what you have to do, you have to take one symbol at a time, plug it in the formula like C, it will be P, then W, then U, and all that. K2, K1 you know, and this computation you do, and you will get the plain text symbol you will get. And so that we will not be doing now because it's very big. But yeah, you can try it out, and I think there are we can make programs also for that. There are some inbuilt Python libraries or third-party Python libraries we can use to do this computation for us. Or you can write a Python program which will do the computation for you. That is very interesting. And then you will get something like this. When we will decrypt it, this is what we will get. The plain text.
Yeah. Got it.
Yeah. So the plain text will be best time of the year. Best time of the year is spring.
Best time.
When flowers bloom. So this is the plain text. So if we have the ciphertext and if we have the key K1, K2, and when we decrypt, we will get a meaningful plain text. And hence we can say that, okay, whatever key we have identified, or that is the right one.
Yeah.
Isn't it?
Yeah.
So see how now we are decoding the mindset of the attacker. Like this is how attacker attacks a system, gets into the system.
Yeah.
Affine cipher we did completed. So cryptanalysis of affine cipher. Like now you got an idea how this chosen plain text attack is so powerful. Like it works. We chose only 2 characters, and if we choose many characters like some big text, we can get some more good results. And whatever ciphertext we got, we applied the formulae over there, and with this technique we were able to break the system, isn't it?
Yeah.
Now the idea is that whatever techniques we discussed, additive ciphers, multiplicative ciphers, and affine ciphers, they all are monoalphabetic substitution cipher, and they have a very small key domain. This is concerning. They are vulnerable to brute force attack. Now we will discuss one more very important concept: how to overcome brute force attack, or how to safeguard the system from brute force attack. And this we are discussing in monoalphabetic, like in the context of these 3: additive cipher, affine cipher, and multiplicative cipher. We are discussing in terms of these 3 techniques because they have a very small key domain.
Yeah.
Now the solution is very simple. Instead of using a fixed key for all symbols, like in all the 3 techniques which we discussed, we saw that there was a fixed key like K1. So that K1 is getting operated with all the symbols. So instead of using a fixed key, what we will do, we will use a mapping. We will use a mapping of keys. What it means, I will tell you. We will use a mapping like whenever we get A, we will map it with a capital N. B, we are mapping it with O. Like we can do any random mapping. So this mapping table we will make. C, we will map it with capital A. Then D, we will mapping with capital D, like any random mapping we are doing. Similarly, E, we will map with R and so on. All the characters we will randomly map it. And it should be one-to-one mapping. Like if N is mapped, then N cannot be mapped with any other alphabet. Then
Yeah.
small z we will map it with W for it. Small y we will map it with capital S. And so this is the plain text. This is the cipher text. Now very interesting thing is that now for encryption I will be making use of this table, and for decryption also I will be making use of the same table in the reverse order. Like if I am getting capital R, I know it is E. Now what the problem the attacker will face? See, now the attacker, let us suppose he has a capital N, for example.
Yeah.
So now, in order to identify the key, the attacker has to identify this table. He has to predict this table, and it is so difficult because in the first attempt he has 26 options.
Second 25, third 24, like that.
Like that.
Order.
That is right. Order.
Cubic number.
Because in the first instant, like for capital N, there can be 26 options, and once it is reserved, like if capital N is for A, then O, capital O will be having 25 options,
Yeah.
then 24. So the key domain, it became 26 factorial, and it is huge. It is huge.
So like here we are not having any key at all, because keys for every letter there is a different key. Key varies from letter to letter. So there is no specific key in this method, right?
No, here key is there, na. Here the key for every letter there is a different key here.
Yeah, every letter there is a different key.
Yeah, but key they are having for A, the key is N itself. Like here, the table which we are using, mapping table, it is containing all those N number of keys. So here we are not using any mathematical operation like addition, multiplication, or combination of that. Here we are just using the concept of mapping.
That's what I was telling.
Every alphabet, every letter will be having a key.
Yeah, like by key I meant like for previous questions we had na key K1 equals 11, K2 equals 4. So like that. Here I was telling for A the key will be suppose 14. For B key will be 13. C key will be 11.
Yeah, that is right.
For each letter there will be a different key.
There will be a different key.
So what we do that, so that we have 26 keys. So do we like okay, so do we send all these 26 keys through the secure channel?
No, through the secure channel we will just pass this table.
Yeah, okay.
So both the receiver and the sender, they should have this table, and using this table we can very easily encrypt and decrypt. And it is almost impossible for the attacker. Like 26 factorial is a very big number.
Yeah. So earlier
to the size was just
like earlier what was happening was they were sending the key through the secure channel only, but the hacker was somehow analyzing the ciphertext and himself choosing a particular key and like chosen ciphertext, himself choosing a particular ciphertext and then predicting the key by himself. But now there is no chance of predicting the key because every letter has a different key.
And also look at the size. Now earlier, no, predicting and all is a different method. Here we are just focusing on the brute force. In the brute force, he is not making any educated guess. He is trying all the possible keys in the brute force. So the idea is that earlier the size of the key domain was just 26 or 12.
Yeah.
So easy to try all the 12 keys or 26 keys. In just seconds we can do that. But in this technique, we increase the size of the key domain. So he can predict this table. It is not impossible, it's possible. He can predict that table, but he has to do 26 factorial computations.
Yeah.
26 factorial computations he will do. Then one of them will be the bingo movement, Eureka movement, wherein he will be able to find the perfect mapping. Yeah. And it is like bit difficult, huh? Like we have increased the complexity of the problem to the next level. And
Yeah.
we can say that, okay, we somehow safeguarded the system from brute force attack. So
Yeah.
mono alphabetic ciphers, they can be safeguarded from the brute force attack only when we use this mapping technique.
Mapping. Okay.
For this technique, isn't it?
Yeah. Mapping. Yeah. Yeah. For monoalphabetic, this is the only way to protect it from brute force attack.
Yeah, that is right. And unfortunately, mono alphabetic ciphers, they will always remain vulnerable to statistical attack, because in this method also the frequency is preserved. Like
Yeah,
if
because one-to-one
yeah,
mapping.
one-to-one mapping. So I can say that mono alphabetic ciphers being one-to-one mapping are always vulnerable to
Statistical.
statistics, isn't it?
Yeah.
So finally, we completed this mono alphabetic ciphers
Yeah.
in this lecture. Now
Yeah.
we have to look at polyalphabetic ciphers and some interesting examples of that. And later on, like some more advanced concepts we can look at. Symmetric key cryptography, we saw mono alphabetic ciphers. The main advantage or the main property of that was it supports one-to-one mapping.
Yes.
One-to-one mapping. So every symbol is mapped any unique cipher symbol.
Yes.
Now the problem with this technique is that it is prone to statistical attack because we cannot hide the frequency.
Yeah.
If let us suppose capital N or letter N in the original text is converted into the cipher text, we can see that, okay, a particular character is repeating N number of times, because that cannot be hidden in this
Yeah.
mono alphabetic cipher. That is very clear to us. So to overcome that, there is another technique, that is the polyalphabetic ciphers. So that is what we will discuss today in the class.
Okay.
So let us start with that polyalphabetic ciphers. So I am sharing the board, just a minute. So it is loading. The board is loading. Can you see the board?
Yes, sir.
Okay, nice. So now we are good to go. We are good to start with the polyalphabetic besides the mono. Let us start. Today we will be discussing polyalphabetic ciphers.
Yes.
As we discussed in polyalphabetic ciphers, there will be one-to-many relationship.
Yeah.
And because of that one-to-many relationship, it is not prone to statistical attack. We can hide the frequency, and it is a very big thing for us.
Yeah.
It's a very big polyalphabetic ciphers. The main property of polyalphabetic cipher, a relationship between a character in the plain text, relationship between a character in the plain text to a character in the cipher text is one-to-many. Cipher text, one-to-many. Okay, this is the main. It means that we can say that, because of which we can say that each occurrence of a character can be mapped to different substitutes. Each occurrence of a character may have a different substitute. Okay. Now, what advantage we will get is, because of this, the main advantage we get is hiding of the frequency, hiding the letter frequency, hiding the letter frequency of the underlying language or of the underlying plain text. Okay, and hence we can say that safeguarding the system from the statistical attack. Safeguarding the system from statistical attack. So this is the main idea behind polyalphabetic cipher. And since because of this one-to-many mapping, we are interested not only in the mapping but also the position of the plain text. So the idea is that in this polyalphabetic cipher, each cipher text alphabet or each cipher text character depends on two things: plain text character also, because we will be converting based on the plain text character only, because the mapping will be based on the plain text only, and also the position, plain text character, and also the position of the plain text character. in this polyalphabetic cipher, instead of using a single key, because in monoalphabetic we saw that we only use single key, and hence it was prone to brute force attack. But in polyalphabetic cipher, we will not be not using a single key, but we will be using a stream of key, and we call it the key stream. Key stream. And what is this key stream? Every character of the plain text, there will be a corresponding key for that. For every position in the plain text, there is a key. So what we can say here is that this ki, let me write it, this ki which we have, this ki is used to encipher the ith character in the plain text, to create the ith character in the cipher text. Ith character in the cipher. So this is the idea. Okay. So now we got a basic idea about what you say that polyalphabetic ciphers, basic properties. Now we will discuss some different types of polyalphabetic ciphers, like some examples. So the first polyalphabetic cipher which we will be looking at, it is the auto key cipher. It's the auto key cipher. The first very important polyalphabetic cipher which we will look at is auto key cipher. It's a very interesting cipher. Here, auto key has a special meaning. Auto key means the key is generated automatically. The key which is generated, it is generated automatically. How it will be done? We will look at it in detail. Now, this auto key cipher, we also call it like simple. We also call it like simple polyalphabetic. Simple polyalphabetic cipher. Simple polyalphabetic cipher. Now, in every polyalphabetic cipher, our objective is to determine the key string, because we have seen that there will be not one key, but there will be a key stream of key, where every key will be the key for the ith character in the plain text. So that key will be used to convert the ith character in the plain text into the cipher text, into the ith character of the cipher text. So our idea is to find the key string. Our idea is to find the key string. Now, how we will do that? Let us see. Now, here K1 is, which is the first sub key. K1 is the first sub key. It is basically any number, like it can be any character. It can be any character. Like first sub key can be like K1 can be any character agreed by both. Any character agreed by sender and receiver. Sender and receiver. Isn't it? And the subsequent subkeys. So K2 will be the first plain key. K2 will be the first plain key. First the plain character, not key. First plain character. First character in the plain text. One example we will discuss, you will get a very good clarity, very easy. First character of the plain text. K3 is the second character of the plain text. Similarly, K3 will be the third, and so on. Let us look at one example to get an idea. Before that, let us look at the formula, like the mathematically, how we can define this. So let us suppose I have plain text P, which is containing some sequence of characters like P1, P2, P3. So the P1, P2, P3 are the characters in the plain text. And I have C is equal to, C is the cipher text. And C1, C2, C3 are the corresponding characters in the cipher text. So P1 got converted into C1, P2 got converted into C2, P3 got converted into C3, and so on. And definitely a stream of key will be used for the same. So we will be using. Now the interesting part is that for the auto key, the first key, like K1, it is any random number, any random character which is agreed by both sender and receiver, but all other subsequent will be the characters of the plain text itself. So the second subkey K2 will be P1 itself, third then P2, P3, and so on. And hence it is called auto key. Why auto key? Because only K1 is the one key which we have to decide upon, and rest all the key is generated automatically. The characters of the plain text will act like the key. For encryption, we will use one formula that we will discuss now. And for decryption, we use one formula. So for encryption, we have because the result of encryption is CI, ciphertext. Yeah, so CI is the ith symbol of the ciphertext. It is PI plus KI, mod 26. So it is also like an additive cipher, but only difference is that here we are having a different key for every symbol. That is the KI. And for decryption, when we are decrypting, PI is the one which is our result. So this PI will be in decryption is the reverse of encryption. So reverse of addition is subtraction. So CI minus KI mod 26, isn't it? And here we can see that it is exactly acting like additive cipher of the mono alphabetic substitution. But here the idea is that multiple keys are used. Every symbol will be having a different key. And here the key is generated automatically. Only the first sub key K1 is the one which we have to agree, which should be agreed by both sender and receiver. And rest all other keys are symbols of the plain text itself, like P1, P2, P3, and so on. Now let us look at one example to simulate this. Then it will be very clear, like how it works. So let us assume that. Let us first write one example, like discuss one example. Now see, we are assuming K1 because K1 is the first subkey should be agreed by both sender and receiver. We assume that K1 is 12, which is agreed by both sender and receiver. And we have a plain text P, which is attack is today, something like that. Attack is. Now we have to use auto key cipher technique for encrypting and decrypting it. So let us encrypt it. So before that, we have to use that table of that letters. This table we have to do. Let me copy this. Let me take it over. Just a minute. Now we will make use of this table to do the encryption and decryption. Let us do it. Let us do it. Idea is simple. Idea says that first we have to write all the plain text characters because here the position also plays a role. So let us make use of that position also. So we will be having a plain text. So here the plain text is having letters like A, T, T, A, C, K, I, S, T, O, T, A. Okay. Now it will be okay. Now what we will do, we will convert this plain text into corresponding numbers and we will call it like P's values. So when I will convert it into number, I will get something like this 0, 0, 19, 19, 0, 0, 0, 2, 1, 0, 0, 8, 1, 8, 1, 9, 14, 0, 3, 0, 0, 20. Now what we will do the key stream. So the key stream will be very interesting to see here. We know that K1 will be the one which we have agreed upon, that is 12, and rest all will be the corresponding plain text itself. So 0, 0, 1, 9, 1, 9, 0, 0, 0, 2, 1, 0, 0, 8, 1, 8, 1, 9, 1, 4, 0, 3, 0. So key stream we got. Now we have to have the C value. C value we can get from the encryption formula. C's value we can get from encryption formula. Encryption formula. And let us see the encryption formula. So Pi plus Ki mod 26. So basically we have here Pi also and Ki also. So 0 plus 12 mod 26 will be 12 itself. 19 plus 0 mod 26 will be 19. 19 and 19 mod 26, it will be 12. It will be 19 itself. It will be 2. It will be 12. It will be 18. 18 and 8, it will be 0. 19 and 18, it will be 11. 14 and 19, like 14 plus 19 mod 26, it is 7. 14 plus 3 mod 26, that will be 17 itself. 3 plus 0 mod 26 will be 3. 24 plus 0 mod 26 will be 24 itself. Now we will get the corresponding cipher text because C value, if we know from the table, we can get the cipher text. We can get the cipher text. The cipher text which we will get, that is something like this. The 12 is M, capital M. Then T, M, T. Okay. Then 2 will be C, M, S, A. C, M, S, A. L, H. like we are referring to the same table, like 7, it is H we are using, RDY. So using this auto key technique, we were able to do a encryption. Now, if we try to do the, and yeah, here one very interesting thing you can see, very interesting thing we can see is that, see TT, it is TM. So the frequency is hidden. Frequency is hidden here. And here AA, and here but MT. And here one more T is there, it is given L. So definitely we have seen that this auto key cipher, what benefit we get is that it hides the frequency count, and hence it safeguards the system from the statistical attack. Just so let us try to do its script analysis to get more clarity on this. So cryptanalysis of auto key cipher. Okay, cryptanalysis of auto key cipher. So it is evident that we have just seen auto key cipher hides the frequency count, or hides the single letter frequency, hides the single letter frequency, statistics of the plain text. Okay. Apart from that, now here one more very interesting observation we will make in terms of brute force attack. If we try to analyze the brute force attack, it is prone to brute force attack. In terms of brute force attack, I can say that it is prone to feasible. Brute force attack can be done. And why is it so? Let us see that. See, idea is very simple. Like, see, we know that it makes use of the key stream, and the key stream, only the first key is the one which is a random character. All other are simply the plain text symbols. So the idea is that we just have to identify this K1, because all the rest will be automatically we will identify now, because that can be identified. So this for this we have option. Like, how many options we have? 25 options. So for K1, we have to make a guess from 1 to 25. That's it. Because the same key will be used for decryption also. No? The same key stream will be used for both encryption and decryption. So now with this drawback, we can say that there is a need. There is a need for a polyalphabetic cipher with large key domain. There is a need for polyalphabetic cipher. There is a need for a polyalphabetic cipher, large key domain. Okay. So this was auto key cipher. Now we will discuss Playfair cipher. Like, we are discussing polyalphabetic ciphers. The interesting property of polyalphabetic cipher is that there is a one-to-many mapping between the symbol in the plain text and the symbol in the cipher text. There is a one-to-many mapping, and because of that, this polyalphabetic cipher which we get, it is free from, it is not holding, it is hiding the frequency distribution of the characters, and it is safe from statistical attack.
Yeah.
And we already looked into the auto key cipher, and it was facing the problem of brute force. Its key domain was limited and it was prone to brute force attack. So now we are in search of a cipher technique, a polyalphabetic cipher technique, which can help us in safeguarding brute force also, brute force attack, which can provide us a very large key domain. And in this direction, we have a very interesting cipher, that is the Playfair cipher, and we will discuss that. So the second cipher technique we are discussing, that is the Playfair cipher in polyalphabetic. Playfair cipher. So what is the idea of Playfair cipher? Let us look at it. And it is so popular cipher, Playfair cipher, it was used by the British Army during the World War I.
Okay.
Yeah, it was used by British Army during World War, and hence it's very interesting. Let us decode it. So the idea is that every time we have a different random distribution of the key.
Okay.
Every time there is a random distribution of the key. In what sense? Let us look at that. So there is a 5x5 matrix.
Okay.
Let me draw that matrix. In the Playfair cipher, there is a 5x5 matrix, and that 5x5 matrix is a random arrangement of characters or the symbols, and that gives us the secret key. Okay, so let us. So it's okay if you are not doing like getting a perfect matrix. It's fine. We just have to understand it. So 5 cross 5. So the idea is that every time we will be having some random characters in it.
Okay.
L, G, D, D, A, U, M, H, E, C, U, R, N, I, J, F, X, B, S, O, K, Z, Y, W, T, P. So this is like one of the secret key. So see, we know that in total we have 25 character, 26 alphabets, but this 5 cross 5 matrix, it can accommodate only 25 characters. So
Yeah.
I and J, they will always occupy the same block. Okay, I and J, and they can occupy any of the block, any of the block they can occupy. Every time they will occupy a different block, and that is the main idea of Playfair cipher. In Playfair cipher, every time we have a different distribution of the secret. Now, how to use it? That is the main idea, na? Like how to use this secret key for encryption, decryption. That we will learn.
Yeah.
Now, some considerations we have to look into that I will write. The first very important consideration we have to look into is that if two characters, if two letters in a pair are the same, if two letters in the plain text, if two letters in a pair are the same, if it is so, then I have to introduce a bogus letter to separate them. Idea is that let us suppose I have A together. Like in the plain text, I have a sequence of words in which I have A together. So if two letters are same, then I have to separate it. I can introduce any bogus letter in between them.
Science.
Hello?
Hello? Yeah.
Right.
Sorry. My phone came.
Okay. So this concept is clear.
Yeah.
Second, after inserting this bogus letter, after inserting bogus letters, if the number of characters is odd, if the number of characters in the plain text is odd, add one extra bogus letter at the end. Add extra bogus letter at the to make it even. Make it even. So these two considerations we have to just focus on. So whenever we are dealing with Playfair cipher, whatever plain text we have, if in that plain text the same characters are nearby with each other, adjacent to each other, we insert some bogus letter, one bogus letter we insert in between them. And if the total length or total number of characters in the plain text is odd, we add some bogus letters in the end to make the length even. Now, three rules we have to use. Let us look at the rules. For encryption and decryption, we have to make use of three rules. So first, we have to take two letters in a pair. Like we have to analyze two letters. So we have to analyze a pair, and according to that, we have to make a decision. If two letters in a pair, so three possibilities are there. The first possibility is located in the same row. Let us suppose I have two letters in the sample text like L, B. Now in this secret key table, L and B, they are located in the same row. So this condition will satisfy. And if it happens, then what I should do? Next character or next letter will be the cipher symbol. Cipher letter will be the cipher. For example, what I have to say, if the plain text has the two letters L and D adjacent to each other, then the cipher symbol for that will be G and B. Plain text is, let me write in the different color. If the plain text is having two letters L and G, then the cipher text will be having, L and D. In the table, L and D, they belong to the same row. And if they are belonging to the same row, so the cipher text will be, for L, it will be G, and for D, it will be B. Next character will be the cipher. Second rule, rule number 2, located in the same column. If two letters in the plain text, they are located in the same column, then next character will be, next character down the column. Next character down the column will be the cipher. Let us suppose the plain text is GB. The cipher text will be, so G and B, they are in the same column. So it will be M and Y. because next character down the column for the G is N, and for V it is Y in the table. So this is the rule 2. Now the third condition, located not in the same row and same column. If they are not located in the same row and same column, then what I have to do? Intersection of row and column, intersection of row and column character, a plain text letter of plain text letter. Okay. Now how we will do it? Let us see. Now let us suppose I have two symbols in the plain text like G and O. Now definitely this G and O, they are neither in the same row and the same column because both are in different. G is here, O is here. What I will do? First, for the G, what will be the ciphertext? Let us see. So for the G, what I have to do? The column is this, okay. And for the O, the row is this. So the intersection is the V. So we have to consider V. And that we will look at one example. It will give us clarity. So now let us look at one real example to get an idea. Let us suppose we have to encrypt plain text hello. Let us suppose plain text is hello. Key is given to us. Let us take this, copy it. Now what we have to do? We have to do the encryption and decryption using the playfair cipher. So the first step is to break the plain text into a pair of two characters. Let us do that. So first we will break it into HE, then LL, then O. We have already seen that whenever we have same letters adjacent to each other, we introduce a bogus letter. It will become, after introduction of bogus letter, it will become HELXLO. Now, since even length, it's okay. And if it would have been an odd length, one extra character in the last, we have to insert. Now, what we have to do? Each pair, we have to convert it into the ciphertext. Let us do that. Using the three rules which we discussed. So first we have HE, then LX, then LO. We have to convert it into the ciphertext. How we will do that? Let us see. See, HE, you know that. Look in the table and we can see that H and E, they both lie in the same row. Isn't it? So we have seen that if both of them in the same row, the adjacent characters will be the cipher. So for the H, it will be E itself because adjacent to H is the E, capital E. And for E, it will be C. EC will be the cipher for this HE. Similarly for LX, if we want. So first identify LX. So you can see here, they both lie in the same column. So down the column, for L, we have capital Q. It is Q, okay? It's Q. And for X, we have capital Z. So this is the cipher for LX. And for LO, L and O, we can see that they are random. L and O, they are random. So see, from O, draw a vertical line. And from L, draw a horizontal line. So the intersection is the capital B. And that capital B is the cipher for capital L or L, small l. So for L, we have capital B as the cipher. And small o. For small o also, we have to do the same exercise. Draw a horizontal line and a vertical line for L. The intersection is the X. And hence, capital X will be the cipher for the O. So this is the ciphertext we got. So the idea is that in playfair cipher, hello will be converted into this ciphertext. And this is so interesting that this secret key which we have, it is totally random. Every time we can have a different secret key. So it is just like magical. And hence it was used in, it is used by British Army in World War I because it is highly secure. It is very difficult to break it. If we try to do the cryptanalysis of this, cryptanalysis of playfair cipher, you will see that cryptanalysis of this playfair cipher, if you are doing, we can see that it's very efficient. Why? Because the key domain, you know what is the key domain here? 25 factorial. 25 factorial is a very big number because the idea is that every box can be filled with 25 base. Like in order to predict a key, what I have to do? Every box, like this character I have to predict, there are 25 base for that. And once I predict this, For this 24 ways, then 23 ways, 22, 21, 20. So 25 factorial. And 25 factorial is a very big, and hence brute force is very difficult. And also it hides the frequency, which is the nature of the polyalphabetic cipher. It hides frequency. Okay.
Okay.
Is it clear how it is working? Play fair.
Yes, sir.
Single letter of the characters. Okay. Now we will do the next one. So a very small break I will take.
Yes.
Then we will be back with the next technique.
Okay.
Hello.
Yes, sir.
Yeah, let's start. Now we will look at the next cipher, third cipher. It's the beginner cipher. You know how to pronounce it?
No, sir.
Give it a try.
Our teacher used to say Visionaire cipher.
Visionaire.
Yeah.
Okay, so let us keep it that Visionaire. So Visionaire cipher is easy to understand. Here the idea. So see, in polyalphabetic cipher, one very interesting observation you might have seen that the key is not same. We can
Okay.
use different keys.
Yeah.
Visionaire cipher. So here the idea is that in Visionaire cipher we have a key string. The key is different, meaning that for every symbol of the plain text there is a different key. As in the previous auto key also we saw that for every symbol there is a corresponding key.
Yes.
And in the playfair cipher also we saw that for every pair of symbols we have a unique key using which we encrypt it.
Yeah.
But earlier in the monoalphabetic cipher there used to be only one key for all the symbols.
Yeah.
And here also in Visionaire cipher also for every symbol or every letter in the plain text there is a corresponding key using which we will encrypt it into the cipher text.
Okay.
So key string is a repetition of an initial secret key string of length n. Okay. And here we have this n can be 1 to 26. So the idea is that we have a stream of keys, and every stream will be of length m, and this length m can be either 1 character, 2 character, 3 character, or 26 characters. It will make sense. With an example, we will get to know what I'm trying to say. So let us suppose I have a plain text p is equal to p1, p2, p3, ... c is equal to c1, c2, c3, ... and capital K is equal to, so this capital K is the key, and this key will be the stream of keys which will be repeating, and this stream of key will be can be of length m. So K1, K2, Km, and it will repeat K1, K2, Km, and it will repeat. Now here encryption.
Sir, let K equals K1, K2, Km. Then K1, K2, is it Kn?
M.
M only.
That's the same. Whatever is here, it will repeat.
Oh, okay. Repeat.
It will repeat. So key stream of length m, it will repeat. Now how it will repeat and like what is the significance of that we will get to know very soon. With one example, it will be very clear. Now in encryption the formula is Ci is equal to, let me write it in the chart. Encryption I have Ci is equal to Ti plus Ki. And for decryption we have something like Pi is equal to Ci minus Ki, isn't it? This is the formula.
Okay.
And the very important point is that this K1, K2, Km initial secret key.
Yeah.
This initial secret key, it is a random secret key which is agreed by both the receiver and the sender. So we can call it like initial secret key.
So like the receiver or sender fixes it and sends it to the other. Right?
Yeah. Initial secret key. Yeah, that's right. Initial secret key agreed by both means receiver and sender. Initial secret key agreed by both receiver and sender. Okay. And this makes it very interesting because in auto key, what was the drawback? Only the one character, only the first key was agreed. and rest all the K2 to KM. It was basically the plain text itself.
Yeah.
But here, a key stream of n length is agreed, and that is repeated, and hence predicting the key will become difficult, and hence it is interesting. Like,
Okay.
yeah, breaking will be difficult, breaking the code.
Okay.
So the key stream does not depend on the plain text character; it only depends on the position. Let us look at one example.
Oh, so it does not depend on the plain text. So it's not difficult to break.
It is very difficult to, because we can agree into anything, na?
Yeah.
Like they can decide any random key.
Yeah.
Now breaking that, identifying that is very difficult.
Yeah.
Now let us look at one example. This example will give you some clarity, like what is happening.
Okay.
Let us suppose P is the message, plain text. She is listening. She is listening. P is the plain text. She is listening. And key, let us suppose key is something like this, Pascal. Okay. Now we have to encrypt it using the Vigenère. So for that, first let us copy that table, this table. Now see what we will do. Now we know that we have the plain text. Let me write it properly. I have the plain text. Then I also will be having the P's value. Then I will be having the key string, which is the Pascal. Then we will be having the C's value, like cipher's value. And finally, we will be having the ciphertext. So this is the encryption we have to do. Now, how we will be doing that? Let us see. S H E I S L I S E E N I N. She is listening. Now the P value. So from this table, like S is 18, like H it is 7, then 4,
8,
then 8,
18,
18,
11,
11,
8,
8,
18,
18, 19, 4, 13, 8.
13, 6.
These all the letters visible now.
Yeah.
Now the key string Pascal P 15 00 18 02 1115 0018 02 00 11. Oh, sorry. 15 00 18 02. Then once again 00. A small mistake and it's gone.
Yes, sir.
00. 11 15 00 18 02 00. So 1 2 3 4 5 6. 1 2 3 4 5 6. So you can see here it is repeating 1 2 3 4 5 6. So key string is repeating. So 15 00 18 02, then once again 00 and 11, and it is repeating. Now the formula for encryption is Ti plus Ki. No need for any mods 26 and all that.
Oh, the 15, 0, 18, this is like their makeup on the spot, right? No, they decide.
The key, the key which they decided initially.
Yeah, it can be anything, right?
It can be anything.
Okay.
It can be. Now, if I do Pi plus Ki, what I will get? 33.
Pi plus Ki 33.
Yeah, so mod we have to do. Mod 26.
33, so it will be 26, 4, 7. 7.
Is it?
H.
Mod 26 here. For decryption also we are doing mod. So 7, 7, 22, 10, 18, 22, 23, 18, 11, 6, 13, 19, 02, 0.
18.
The final ciphertext which we will be getting is H W K H W X S L G N T C. So this is the Vigenère cipher. So here we saw that the initial key stream of length m, which is been agreed by both the parties, it is repeated m times.
Yes.
And hence decoding it will be very difficult.
Yes.
And hence it is secure. It is more efficient.
Yeah, got it.
Now, like some more scenarios is given that we don't need to consider. Like Vigenère cipher can be seen as a combination of m additive ciphers. Okay, let me do this. Let us not keep anything untouched. At least once let us do. So in Vigenère cipher, which we are discussing, one more thing we can discuss. I can write combination of m additive ciphers. Combination of m additive ciphers. In total, we have 15. Let me do manually. S H E. She is listening. Is something is wrong. It's a bit slow. Listening. NING. She is listening. Now we know that the key is of Pascal. That is 6 length. So after every 6 character, the key will repeat. So 1, 2, 3, 4, 5, 6. I can shade it with a different color. 1, 2, 3, 4, 5, 6. Now we know that this, and this the key will be same because P, and whatever the value of the P, that will be the key. So I can say that S I, this plain text will be mapped to the key P because key is Pascal, so it will be mapped to P. It will be mapped to P. Similarly, HSN, HSG, sorry, second, HSG, it will be mapped to the second key, that is the A, Pascal, A. Then ET, it will be mapped to S, Pascal. Then IE.
Sir, sorry, I lost it. Like when how is SIN mapped to P, HSG mapped to A? How is it?
Okay, I will.
Oh, sorry, Pascal. Oh, like that. SIN HSG. Okay. ET. Then IESNLI.
Yeah, now you got it. Then we have SN because after every 6 alphabets letters, it is repeating the key.
So for S, I, and N, there will be same key.
Yeah, for the first, because the color shading, it is representing the group. So the first letter of all the groups, they will be mapped to P,
Yeah.
PASCA. The last, the LN, LLI, sorry, LI. It is the L. Now what we will get is we will get cipher text. So when I will add S with P, I with P, N with P, I will get different cipher text. I will get HXC. Here I will get HSG. Here I will get WL. Here I will get KG, SN, WP. So basically what we did, the encryption process, we converted into 6 additive ciphers because the key size is 6. So every key like P, it is an additive cipher. The key with A, it is a additive cipher. So we got that.
Sir, I did not understand what we did here.
So see, the idea is that now it is said that the beginner the cipher which we are discussing,
Yeah.
if the length of the key string is m characters,
Yeah.
then that cipher can be converted into a combination of m additive ciphers, and that we have shown for this example, wherein we have the key stream of length 6,
Yeah.
and hence we have 6 different additive ciphers. Like
Okay.
this is one additive cipher, this is second additive cipher, this is third additive cipher, this is fourth additive cipher, this is fifth, this is sixth. So m additive cipher, we converted it. Now whatever answer we got, now we will combine it smartly. Now how we will combine it, I will show you. Now we will combine it in such a way that all the first letters, they will come together. Let me follow the color convention. So green. Sorry. Okay. Let me write the answer, then I will shade it. So first, all the first letters, let me write it. CG. 1, 2, 3, 4, 5, 6.
You missed a T.
No, in the
Oh.
here, in encryption no T. Then here, 1, 2, 3, 4. CG.
Oh, it's a P, I think. P or T?
P. After N, it is P.
P.
P for parrot.
Then here you wrote wrong in cipher text.
No, no, ciphertext is right. Now let us compare it. Okay, here I have wrote down. It is P.
Yeah.
It is P. Let me correct. So we got the exact answer. So once again, I am telling you what I did. See, ultimately, whenever Vigenère cipher they are asking, or we have to demonstrate that this is the right way, wherein whatever text is given, just write that, and key, just write it and repeat it until the last word, and just add it, and mod 26 you do, whatever you will get, convert back into the ciphertext. You got the answer. That is very fine. But if we want to demonstrate Vigenère cipher as a combination of m additive ciphers, for that what we have to do, whatever text we have, directly we cannot add the corresponding letters. You make it one group. So first, so you make a group of key stream length. Here it is 6. So I made a chunk of 6. Like first 6 letters I gave it a different color. Second 6 I classified it into a different group. Third I classified it into a different group. So different groups I made. Then what I did, first characters from all the group I took, then second character, then third character, then fourth, fifth, sixth. In this way I did. The first block which I get, I will operate it with the first key. The key stream of m length, the first key of that is the P, and I will get the resulting answer, the additive cipher answer. Then A, then S, then C, then A, then N. So corresponding answers I will get. Now what I have to do, I have to just combine the first alphabets of all the blocks. First letter, then the second letter, then the third letter, and I will get the same answer which I got here. So this is another way of doing the encryption. Here we are demonstrating the Vigenère cipher as m additive ciphers.
Sir,
Yeah, tell.
sir, so here, this part, SIN, P is there, right?
P is the key.
Yeah, P is the key. So what we will do is S, we will, if we have to do in this additive cipher way, then S, we have to take first S, the number of value of S, which is 18. Then we have to add P's value.
Yeah.
P is 15. 18, 15, 33, mod 26, 7. So H. Similarly for I, we have to do same thing.
Yeah.
P's value we have to add, and then be X. Then
that is
like that.
Like that.
Oh, okay.
So like that we have to do for all.
Okay.
And whatever answer we will get, that will not be the final answer, but we have to like rearrange the answer. Like first letters, then second letters, third letters.
Yeah.
Okay. Is it clear?
Yeah.
Okay, so now we can start with this Hill cipher. So we are already discussing what you say that poly-alphabetic ciphers, in which we saw that there is a one-to-many mapping. We saw some examples of poly-alphabetic ciphers like auto key ciphers, Playfair ciphers. Now we will be looking at Hill ciphers. Let us look at very important Hill cipher. Now, what is the concept of Hill cipher? The plain text which we have, it is divided into equal size blocks. The plain text is divided into equal size blocks, and the equal size blocks, they are encrypted one at a time. So this plain text is divided into equal size blocks, and these equal size blocks, they are encrypted one at a time. Encrypted one block at a time. Okay, and during the encryption, one very important thing we should consider is that each character in the block, equal size block, so each character in the block contributes to the encryption of other characters in the block. And this is a very important property. With example, it will become very clear whatever we are discussing. But now just note it down. Let us note it down. Each and every character in the block, contributes to the encryption of other characters in the block. So the idea is that the encryption process, it is dependent on the plain text also here in the Hill cipher. Just like in the auto key cipher, here also the encryption, it depends on the position of the plain text characters as well as the plain text character itself. So both of them play a role in the Hill cipher. Isn't it? Hill cipher, basically, it is also called as block ciphers, or we can say that Hill cipher belongs to a special category of ciphers, that is the block ciphers. So in the bracket, I can write for Hill ciphers, I can write it. These are basically block ciphers. Very equal size blocks are created, and each block is encrypted one at a time. And during the encryption process, the characters, each character in the block is utilized. It plays a role in the encryption of other characters in the block. So we got some basic idea about the Hill cipher. Now, in this polyalphabetic ciphers, whatever ciphers we studied until now, those are the stream ciphers. Like the auto key cipher, it's a stream cipher, and playfed cipher, it's a stream cipher, and that how you pronounce that? Vigener, that cipher, that is also a stream cipher.
Yeah, Vigener.
Yeah, that's a stream cipher. But this Hill cipher is a block cipher. So first block cipher we are learning, and we will get a very good concept. We will get a very good concept of how the block cipher exactly works. So before getting into the working of the block cipher, first let us discuss some basic mathematics or mathematical concept which will be involved in the Hill cipher. So let us look at that. So the mathematical aspect of the Hill cipher, very important discussion here. So in any of the cipher technique we study, the mathematical aspect, it involves two things, encryption and decryption. Like the formula to encrypt, the formula to decrypt, and the key, how to choose the key. So three aspects we have to define. What is the encryption algorithm? What is the decryption algorithm? And how to choose the key. Let us try to unlock that. Encryption, decryption. Now see, in the encryption, we get ciphertext as the result always. So I can write it. So ciphertext as the result, and input will be the plain text in the encryption. So there will be an encryption function which will take the key along with the plain text to give me the ciphertext. And this encryption function is nothing but it is P into K mod 26. P into K mod 26. This operation. With an example, we will get an idea how it works. Similarly, for decryption we have D is equal to, okay, for when we decrypt, what we get the plain text. So plain text is a function of decryption algorithm. It will take two things. It will take the key and the ciphertext. It will take the key and since we are discussing the private key cryptography, both the sender and the receiver, they will be sharing the common key. Very important discussion I am making. Until now, whatever techniques we have discussed, both the sender and the receiver, they have the common key with them. The key is same for both. And the formula will be the ciphertext, whatever we have, that we will take that and we will multiply it with the K inverse. And we do the mod 26. I can write it like this also because C, I know C is already P into K mod 26. So I can write C as P into K inverse mod 26. Now in a Hill cipher, these encryption, decryption, formula representation, I can convert it into a matrix because the key will be a block. It's a block cipher. It's a block cipher. So the key will not be a string, but it will be a sort of a block kind of a thing. So I can convert it into matrix form. Let us do that. In the matrix form, we will have something like this. In the encryption, for the encryption, we will have C1, C2, C3. That is the ciphertext. It will be equal to the plain text characters P1 because the formula, what is the encryption formula? Plain text into key. So P1, P2, P3. Like I am taking one block. Let us suppose in the block I have 3 letters. I am taking a block of size 3 because it's a block cipher. So these 3 letters I will take and I will multiply it with a key. So I will have the key like this: K11, K12, K13, K21, K22, K2, K31, K32. Okay, and I have to do the mod 26, whatever we have. So the encryption formula, I just converted it into a matrix form. Now this matrix, when I will solve this, I will get the ciphertext for these 3 symbols P1, P2, P3. I will get cipher letter C1, C2, C3. Let us give it a try. Let us do one practical example, like whatever we discussed. So let us suppose we have to do a encryption wherein the plain text. Let us do an example. I will write example. In this example, I have a plain text that is pay more money. I have the plain text that is the pay more money, and I have to encrypt it using the Hill cipher. And key is given, and the key which we have, that is the matrix which is given. It is 17, 17, 5, 21, 18, 21, 2, 2, 9. This is the key and the text we have, and we have to encrypt it. Now, definitely we need that table. Let us get that. This table we need for mapping purpose. Let us get this table somewhere here. Now we can use this table to convert this pay more money into number with the mapping. Like P is 15, like this. A is 0. P, A, Y, N, O, R, E, N, O, N. Now, when I will convert it into number using the table, 15, 0, 0, 24, 12, 14, 17, 4, 12, 14, 13, 4, and 20. Now, since the key is a 3 cross 3 matrix, I can break it into a 3, 3 blocks. Because according to the formula, it should be of 3. It should contain 3 symbols because the key is 3 cross 3 matrix. 1, 2, 3, 1, 2, 3, 3. And I can encrypt it separately. Now, how I will encrypt it is very easy. I just have to multiply this with the key, like 15, 0, 0, 24 with the key, then 12, 14, 17 with the key, 4, 12, 14 with the key, and 13, 4, 24 with the key. Then I will get the ciphertext. The 3, 3 ciphertext I will. So let me write it, what I'm trying to say. Let us do this operation. So what I'm trying to say is that in order to encrypt the pay, what I have to do is I have to multiply 15, 0, 0 and 24 with the key itself. 17, 17, 5, 21, 18, 22, 2, isn't it? Then like this multiplication you can do, and we know that it is 1 row 3 column. Like this matrix is 1 cross 3 and this is 3 cross 3. And when we multiply, once again we will get 1 cross 3 matrix, like 1 row 3 column. And that 1 cross 3 matrix will contain 3 numbers. That will be the ciphertext, the number for the ciphertext. And when we will convert it into the alphabet, we will get RRL. Now this multiplication, I am not going to do it now. It will be very time taking. That you can try, but you can cross check it. After multiplication, whatever numbers you will get, if you will convert that into the alphabets, like for your reference, I can help you with that. So it will be something like 17, 17 and 11. So this is the result you will get. And this we know that it will be equal to RR. So the pay, this is the plain text. It got encrypted into the ciphertext with this method. Similarly, for all other blocks, same operation will be done. Then we have MOR. For MOR, we have something like this, 12, 14, 17. And we will multiply it with the key itself, which is given 17, 17, 5, 21, 18, 21, 2, 2, 19. And we will get a number like 3 cipher numbers, that is 12, 22 and 01. And the corresponding ciphertext letters will be MWB. So MOR, it got converted into MWB. Similarly, we can do it for other blocks, and in this way we can get the ciphertext. Let us do it because 2 more blocks we have to do. Then we have EMO. This EMO will be something like this, 4, 12, 14, and we will multiply it with the given key itself, 17, 17, 5, 21, 18, 21, 2, 2, 9, and we will get the answer. Answer will be 10, answer will be 10, 0, 0, 18. Like if you multiply these 2 matrices, you will get something like this, and it is KAS, encrypted. Isn't it? Now the last, you can try that, NEY, 13, 4, 24, and we can multiply it with the key itself. 17, 17, 5, 21, 18, 21, 2, 2, 90. We will get the result that is something like this: 15, 3, 7. 15, 3, 7. Like you can cross check it after multiplication, you will get 15, 3, 7. And this is equal to PDH. So we got it. Finally, we can say that if the plain text is pay more money, we have the plain text and we have the corresponding cipher text. The plain text which we have, that is pay more money. And for every letter in the plain text, we have a cipher text letter. That is RRL, M, W, B, A, S, PDH. So this is the answer. This is how, using the Hill cipher, we were able to do the encryption. So here clearly we can see that the cipher text alphabet, it clearly depends on the plain text, because the plain text letter, we are multiplying it with a key, and not just one plain text but all the plain text. So the what I'm saying here is that in a particular block, in order to generate one cipher text alphabet, let us suppose I want to generate C1. Now this C1 is dependent on all the P1, P2, P3. In that block, all the plain text letter, it is dependent on that, because in this computation, when we are multiplying P1, P2, P3, all of these characters will play a role. And that is what we have written, like in the beginning. Each character in the block contributes to the encryption. So every character in the block is contributing, and hence we prove that. Now, one very important point which we should mention in the theory itself, like somewhere here we can mention it. The key which we are taking, the key should have because key is a matrix, but that matrix should have a multiplicative inverse. Otherwise, it will fail. So let us write it down. The key which we are choosing, which is a matrix, it should have the multiplicative inverse. So the key in the Hill cipher, the key in the Hill cipher, the key in the Hill cipher should have a multiplicative inverse. Okay. Now we can do the crypt analysis of it. Let us try that. Just a minute. Let me check whether we should discuss this one. Like one very important discussion we can do. Just in the formula, we can see that in the decryption formula we have the K inverse. It means that using because see, K is a matrix and K inverse is the inverse of the matrix. So we know how to calculate the inverse of the matrix. Like we know how to do that. So if I have a cipher text and if I have a K, that is a key matrix, then just I calculate the inverse of it, inverse of that key matrix, multiply the cipher text with the inverse of the key matrix, do the mod 26, and I will get the plain text. And this is how decryption is done. In terms of crypt analysis, what we can see that identifying the key is not easy here, because the key is like here it is like 3x3 matrix in the example. In the example, it's a 3x3 matrix. And now every position we can fill with 26 alphabets. And here repetition of number is allowed because it's a matrix. So 26 ways to fill this position, 26 ways to fill this position, 26 ways to fill this position. So it will be like 26 to the power of, it will be very, very big number. And brute force attack will be difficult here to decrypt, because first you have to guess a K. Then in order to decrypt, calculate the K inverse. And then whatever cipher text you have to multiply it with the K inverse. So it is like a very intensive computation you have to do, and brute force is not easy here. Here brute force is not easy. And if I talk about statistical attack, is this hiding the frequency count? So definitely we can see, like here you can see that we are repeating M, and here also. So here I am having capital M, and here I am having A. So I am hiding the frequency count. And whenever I am hiding the frequency count, I am safeguarding the system from the statistical attack. So in terms of crypt analysis, we have seen that Hill's cipher is efficient. It helps us in safeguarding from the brute force attack also, and from the statistical attack also. So yeah, it is efficient. We can rely on it.